Hi, everybody. So in my first period class today, we weren't able to finish all of the notes today, which is totally cool. We definitely tried to jam a lot into a small amount of time. So I'm going to kind of pick up where we left off for my sixth period class. You're going to get this during class 2, probably about the exact same amount. But I'm going to treat it as if we didn't do anything. You can see I already marked a lot of stuff here, but I'll still address that. I'll talk about what's going on. Now, in terms of other students, so I told Mr. Noble that he should share this with his classes and maybe even Mr. Fossey. Mr. Noble definitely teaches it a little bit differently than I do. So that's why I think both classes will share both teachers' videos, just so we can kind of see two different ideas. And you can choose whichever one you like best. So the big thing you'll see right next to 11.4 planes in space, I have linear equations. This whole section of 11.4, I want you thinking about linear equations. Y equals mx plus b. Y minus y1 equals m times x minus x1, point slope form. Okay. I like to compare planes to lines. And if you really think about it, right, a line is just a segment that connects 2 points, but it continues on and on in 2 directions, right? A plane is essentially an extension of that, a line that now continues on and on and on in every direction. So one of my students in class first period, when I asked about planes, not the flying planes, but other planes, she brought up like the Great Plains or like planes on the ground. And in essence, right, like a flat piece of land that kind of goes on forever. Like there's a correlation between why farmland and flat land are called the plains, right? Kind of, you can imagine just a flat, plane of glass that extends forever. Like, so that's what a plane in a nutshell is. It's a line that continues on in all directions. So not just, this kind of expanding everywhere. And think about a piece of glass. Think about a piece of glass that would go on and on and on forever, what that would look like. All right, so a couple of things here. The equation of a plane, right? This is just your basic equation of a plane. So I compare that to like y equals mx plus b, which is slope-intercept form. Here, maybe we would call this component form. It doesn't really matter, but ax plus by plus cz plus d equals 0, right? To me, that's like y equals mx plus b. I can put it all to one side, right? But the difference is your vector is almost like going to be 3 slopes in a problem. So A, B, C, those come from the vector, the quote unquote slope in my comparison. And then I talked about what did we need to make a line? Well, in order to make a line, you need a point and a slope. Sometimes you get 2 points. You find the slope, pick a point, whatever. So if you think about that, to make an equation of a line, you learned this, some of you probably learned this in like 7th grade, right? You need a point and you need a slope. When you have your point or your slope, you now get to choose which method you go with. Okay, so I have an example of that on my next page. All right, so let's say I give you the point 2 comma 5 and the slope 3 over 2. You have 2 options on what you're going to do here. You're either going to do y equals mx plus b form, right? This is what I compare to ax plus by plus cz plus d equals 0. Or you're going to have this second one, which I compare to the formula a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. Right? These are my kind of comparisons. Both of them work. Noble is more of the left side. Socko is more of the right side. But, so for this left one, if you have a point and a slope, I plugged in 5 for y, 3 over 2 for m, 2 for x, I get b equals 2. The reason that I personally don't like that method when I teach Algebra 1 is a lot of times students, they solve for b, they feel a sense of accomplishment, boom, I solved for something, I got an answer, and they stop. But we know in all reality, if I want the equation, I actually have to now take that b and the m and plug it back in. Well, that kind of concept is eliminated when you do the point slope form because you already get an equation for your answer. You don't solve for a letter and then have to plug that letter back in. So on this same general idea, right underneath where I write in red, to make a line, we need a point and a slope. A plane in 3D is determined by a point and a vector orthogonal to the plane. So underneath that, to make a plane, we need a point and a perpendicular vector. So just like to make a line, you need a point and a slope. To make a plane, you need a point and a perpendicular vector, our plane slope, right? Which is essentially, think about what a vector is. It's a direction and a length in a nutshell. So they're very similar, right? So as I kind of scroll down a little more, I don't want to go too far, to this where I have the blue and the pink highlighting. So our two formulas, we have, for the sake of this, we'll call this component form, because we're just using the component form of the vector. Ax plus by plus c, z plus d equals 0. If you use the blue highlighted method, you're going to have a point, you're going to have a vector, you plug it in. The piece you won't have is d. Just like we solved for b and mx plus b, you'll plug in all the info you have, you'll solve for d, you plug it back in. Not my preferred method. My preferred method is the standard form. Looks just like point slope. A, parentheses, x minus x1 plus b, quantity y minus y1 plus c, quantity z minus z1. Notice there's no d in that equation. Just like in point slope, there wasn't a b in the equation. But when we get to our final answer, we still get the b value. This is no different. So here's one example of that. Write the equation of the plane that contains -5, 1, 0. That's our point, our x1, our y1, our z1, and is parallel to 2x minus 7y plus 13z minus 4 equals 0. Okay, so there is our plane. Whenever you have a plane and you want the perpendicular vector to that plane, you literally just take the three coefficients, 2, -7, 13. There's our normal vector. So if you look at that, my point is x1, y1, z1. My vector is a, b, c. And I literally plug it into the pink highlighted formula. 2 times the quantity x plus 5, minus 7 times the quantity y minus 1, plus 13 times the quantity z minus 0. That is such simple algebra. I know all of you can do it. 2x plus 10 minus 7y plus 7 plus 13 is equals 0. Long story short, here's the equation of the plane that's parallel to that. So you might be confused here by the word parallel. You might say, well, they're talking about parallel planes, but he used a perpendicular vector. Totally would get why that would be confusing. But think about it. The perpendicular vector to 2x minus 7y plus 13z minus 4 is 2, -7, 13. I now found another plane that has the same perpendicular vector, 2, -7, 13. Well, if both of their perpendicular vectors are the same, well, by definition, those are parallel. So don't get caught up on like the fact that it says parallel and we're talking about a perpendicular vector. That's really just saying I have two planes that are parallel, just like a line, right? But instead of using a point, we're using a perpendicular vector, or a slope, I should say. All right. So in Mr. Noble's video, you might have a different way of solving this. I like to stick with my guns. This is the way I like it. Okay, so write the equation of a plane that contains -1, 4, and 2. So here's my x1, my y1, my z1, and the vector is 3, -2, 1, my ABC. Real simple. 3 parentheses x plus 1 minus 2 parentheses y minus 4 plus 1 parentheses z minus 2 equals 0. Now we just straight up simplify. 3x plus 3 minus 2y plus 8 plus z minus 2 equals 0. Shuffle some things around, combine like terms. 3x minus 2y plus z, 3, 11, 9 plus 9 equals 0. So you end up getting that d value anyway. Our d value would be 9 here. Going back a little bit, if I want to know how far our plane is from the origin, which is a little different than a line, I use that formula. Take my d value, divide it by the magnitude of the plane. Pretty simple. Okay, so there's that. These two are the simple ones, right? You got a vector, you got a point, boom, find your plane. No big deal. Sometimes we have a little bit more work to do, all right? So down here, write the equation of the plane containing P, Q, and R. All right, so always ask yourself this. What do we need to make a plane? Well, one, we need a point. In this particular question, we have a lot of these. We have 3 points we can choose from. We also need a perpendicular vector. Well, we don't quite have that yet. We got a lot of points. So this is where you have to combine 11.3 with 11.4. We just learned a way to create a perpendicular vector. We have to do the cross product of two vectors. Okay, well, let's do it. Well, shoot, I don't have any vectors yet. No worry. I can easily make vector PQ, right? So I'm not going to go through the work to do this. At this point, if you don't know how to do a vector, you maybe need to hit asynchronous time a little bit more. PR is 2, 2, 2. Okay. Remember, I got a lot of points. When it comes time, I'll choose one of those three. We'll be good. So I got my two vectors. These don't tell us anything. These don't tell us anything. These are just vectors. I need a perpendicular vector. Well, in order to accomplish that, I'm going to have to do PQ cross with PR. So I got I, J, K, -4, 6, 6, 2, 2, 2. I like to use my highlighter here. It makes things stand. Oops, sorry. Okay, I like to use my highlighter here and go that way. And then I like to use the blue because you see that little overlap. Okay, so now I know this is going to be I times 6, 6, 2, 2 minus J times -4, 6, 2, 2 plus K times, right? And I know I have the luxury of moving this all around, and you don't have that at home, but I think visually speaking, it's pretty cool. All right. So now what this gives me is I times 0 minus J times -8 minus 12 is -20 plus K times oh, that's another 20. -20. So I get my vector of 0i plus 20j minus 20k. You can give me that, or you can say 0, 20, -20. It's up to you. It's your prerogative total. All right. So now we've created our perpendicular vector. So if to write an equation of a plane, I need a perpendicular vector and a point, I now have that. The decision now is, what point do I use? I'm going to choose that point because it has a 0 in it. Any point that has a 0 in it, for me, a little bit easier. So it's real simple now. 0 times x minus 2. 0 times x minus 2. All right, plus 20 times y minus 0 minus 20 times z plus 4 equals 0. Sorry, I'm kind of bleeding into it there. That gives me, well, that's gone, obviously. 20y minus 20z minus 80 equals 0. Now, we can actually divide this all by 20, right? So if I divide this all by 20, I can get a much simpler one to get y minus z minus 4 equals 0. I'm allowed to do that to simplify numbers down, especially when they're big like that, because the 0 on the other side. Okay, so that's our final answer. Now, in the video, you can pause, stop, and start whenever you want. So look at all that. Biggest thing to always ask yourself, if I want an equation of a plane, what do I need? Compare it to linear equations. You need a point and a perpendicular vector. All right. So we don't have that much left. We actually only have a couple questions here. Find the angle between two planes, right? Well, that still uses the same old formula that we did before. Cosine of theta equals u dot v over magnitude u times magnitude v. All right. So let's go ahead and first let's turn these into vectors. 1, negative 2, 1, and 2, 1, 1. All right. At this point, should be straight shooting. U dot v is going to be 1 times 2 plus negative 2 times 1 plus 1 times 1. That actually gives me just 1. Magnitude of u is the square root of 1 squared plus 2 squared plus 1 squared. That gives me root 6. Magnitude of v, square root of 2 squared plus 1 squared plus 1 squared. That's the square root of 6. So now when I take that info and I plug it in here, I got 1 over root 6 times root 6. Oh, that actually works out to be 1/6. Second cosine of 1/6. Second cosine of 1 over 6. Remember, when I'm finding a theta, I always need to second sine or cosine, whatever we're using. I get 80.4 degrees. That's a bad 0. I can do better than that. All right. Pretty straightforward, I would think. All right, and I believe our last question, and planes and vectors are very similar for a lot of things we do, right? So I know that parallel vectors are scalar multiples. I know perpendicular vectors have a dot product of 0. Well, planes are no different, okay? So as I finish up here, determine whether the planes are parallel, perpendicular, or neither. Okay, so as I turn these into two vectors, I got 3, negative 2, 1, and I have 2, 3, 4. Remember, these are orthogonal vectors. Sometimes I skip the orthogonal part and I skip it. So if I call this one A and that one B, it doesn't matter. Can we multiply A or B by anything to make the other? So 3 times 2 times, so 3 times something to make it 2, but the same number. Yeah, so these are definitely not parallel. That's for sure. There's not any sort of scalar multiple there. All right. So now, orthogonal. All right, well, let's do the dot product. A dot B is going to be 3 times 2 plus negative 2 times 3. I like that. Plus 1 times 4. Oh. For this, so I get 6 minus 6 plus 4. Well, that equals 4. So they're not perpendicular. All right. Which, of course, means that they're neither. But looky, look right here. If they are neither, find the angle of the intersection. So I have to actually go ahead and find the angle like we just did on the last question. So luckily we already got the dot product. So if I want to find this angle, pretty straightforward. Cosine of theta, the dot product we got is 4. The magnitude of A is going to be 9 plus 4 plus 1. So I get, sorry, I don't have to write that. Square root of 14 times the magnitude of b is going to be 4 plus 9 plus 4, which gives me the square root of 29. All right. After I do this, I get the angle between them is 78.5 degrees. Literally did the same thing we just did in the question above. All right. I'm sorry. I know this was a little bit long-winded, but that being said, we kind of handled everything. I think a lot of you appreciate videos because you can stop and start at your own pace. So yeah, that's everything that we did. And this is all of 11.4. And hopefully that's everything you need. So I'm going to go ahead and log off here and see you in class.